The topic for this short presentation is prediction and modeling of phase equilibria, where due to the short time span that is being available, basic familiarity with the underlying thermodynamic concepts is assumed. And the main aim is to motivate people to further explore how molecular modeling simulation can be applied to phase equilibrium phenomena. So let us recall, what is it that characterizes a phase equilibrium? In general, multiple phases coexist, and there can either be a pure system or a mixture with a number of components greater than one. And thermodynamic equilibrium is characterized by thermal, chemical, and mechanical equilibrium. So all phases need to have the same temperature. All phases need to have the same chemical potential and mechanical equilibrium to be at equilibrium at a planar surface. All phases need to exhibit the same pressure. And the relation between those quantities can in each phase be characterized by a thermal equation of state. And then what is my aim today is to illustrate that in particular, this is accessible by molecular modeling. So most people will be very familiar with the notion that when you consider temperature at a molecular level, this is the motion, the statistical motion of the molecules. So at a molecular level, this is expressed by the kinetic energy of the molecules. So kinetic energy and temperature are proportional to each other. And in this way, this is easily observable. Either it can be specified or it can be observed from a molecular simulation. The chemical potential is related to exchange of substance, exchange of matter between the phases, or in general between a system and its surroundings, and a technique to determine it in a molecular simulation can be based on a statistical mechanical expression that evaluates how the energy of a system changes when you insert an additional molecule. Statistics over this quantity yield the chemical potential. The pressure has a well-known contribution, which is the ideal gas law. In this case here, this is expressed by the first term, density times temperature. And a residual contribution due to the interactions between the molecules, which is called the virial contribution. It is the sum over the product of force times distance, which is this expression, between all pairs of molecules in the system. So this is also something that can be straightforwardly determined. So if we have these quantities, or consider them, how do they lead us to finding the actual phase equilibrium state? For this, we need to find a point where pressure, temperature, and chemical potential of the involved phases coincide. Now, this on top here is the Gibbs-Duhem equation. And it gives you the chemical potential, total differential for the chemical potential, as a function of pressure and temperature. If we consider the derivative with respect to temperature at constant pressure, that is minus S, minus molar entropy. So here you get, on this basis, diagrams like this for the different phases. The slope, mu over T at constant pressure, is the negative entropy, and the phases with greater entropy have a greater negative slope. And so this leads them to have such intersections. Here you have the solid-liquid equilibrium, here you have the vapor-liquid equilibrium. And this is at constant pressure. Of course, these curves do depend on pressure. It's particularly strongly for the gas phase, because here the density changes very significantly. Density is very significantly dependent on pressure. For a vapor phase, to first order, it's proportional. And for that reason, this is most strongly affected. Now we can also look explicitly at the dependence on pressure from the same equation. The derivative of chemical potential with respect to pressure is the molar volume, or 1 over density. And so if you look at mu over p, then the slope is the specific volume. The lower density phase has a steeper slope than the higher density phase. So this, for example, this could be the liquid and this could be the solid, or it could be the vapor and the liquid close to critical. And there you have an intersection. So if you know the values of the chemical potential and its derivative close to this point, you can extrapolate both curves and determine the conditions at which the two phases are in equilibrium. If this extrapolation is done over temperature, entropy is required. If it is done over pressure, density is required. And the chemical potential is required as a basis. The same applies to mixtures. Only the parameter space, the space of available thermodynamic degrees of freedom, is higher dimensional. If you look at a binary mixture of two components, then what you can already immediately see that can be varied is you can go from pure A to pure B, and you have the composition as an additional parameter. In a ternary phase diagram, where you have three components, then you get triangles like this. So this is more complex, but essentially the same. Only as far as modeling is concerned, this raises an additional problem. If we have a model available for the pure compound, and we want to apply this to a mixture, then in addition to representing the interaction between similar or like molecules at this set, we need a model for the unlike interaction, the interaction between molecules that are unlike. So how is this done? Typical molecular force fields are based on a rough reproduction of the geometry of the molecule, and then a representation of the major intermolecular interactions that there are. Electrostatics, for which Coulomb interaction sites based on Coulomb's law are introduced, and dispersion, also known as the van der Waals force, which is attractive, and repulsion, which are modeled by a semi-phenomenological contribution, which is in the most popular case, the Lennard-Jones potential. What we need to know now is, first of all, that this is not an ab initio approach. It is inexact, and it fuses several types of interactions. It's already one of the reasons why I called it semi-phenomenological or semi-empirical, and it has two characteristic parameters: the length scale of the interaction, the size parameter sigma, and the energy parameter epsilon. Now, if we go to a mixture, electrostatics combines straightforwardly, because the Coulomb interaction applies equally between sites that belong to equal molecules and to different molecules. For the Lennard-Jones potential, that is not so straightforward. If you have the parameters for component A and component B, how do you go over to the unlike interaction? For this, mixing rules are available. The most popular one, for which also a kind of theoretical case can be made, is the Lorentz-Berthelot mixing rule. The size is determined from the arithmetic mean and the energy from the geometric mean. And this is predictive. If you have adjusted the models for A and for B, for example, to phase equilibrium behavior, then on this basis, without any additional input, the phase equilibrium behavior for the mixture can be predicted. Often, it makes sense to readjust the mixture model, and then you get additional binary interaction parameters that modify these rules. These are normally relatively close to 1. So that's it. The time available for this has been short. If there was more time available, I would do a wrap up. What are the main conclusions? The take-home message. First of all, phase equilibrium follows the thermodynamic equilibrium conditions, and this is expressed in terms of the chemical potential for chemical equilibrium, the pressure for the mechanical equilibrium, the temperature for the thermal equilibrium. These properties are accessible to molecular simulation, and there are diagrams where the phase equilibrium state can be found or can be seen, observed as an intersection of several curves representing the coexisting phases. To extrapolate these curves, first of all, the chemical potential is needed as a basis, and then the first derivatives, which is the molar volume or the molar entropy. For molecular models, phase behavior of a mixture can be predicted from a mixing rule, such as the Lorentz-Berthelot mixing rule. And also readjustment is possible by introducing additional adjustable parameters for the mixture. An exercise could be a pair exercise where the participants are grouped into pairs and they are given these diagrams with the question what the properties are, what sort of diagrams are these. Maybe they have been seen before, maybe they are known, maybe one person knows them and the other doesn't, and then they can have a discussion and one can advise the other. And what is the solid phase and what is the liquid phase? And some time could be given also to give people the opportunity to discuss. And that would then be resolved and be discussed. The gas phase was already labeled. The shape of this curve, to people who know vapor pressure curves, already suggests that this is P over T. And at lower temperatures, you have the solid. At higher temperatures, you have the liquid. And there's the triple point where the liquid phase ceases to exist at equilibrium. And the curve, the diagram at the right, is the same one that had been seen before, just with inverted axis. So this is not mu over T, it is T over mu. And the slope at constant pressure, as it was indicated, is then 1 over the molar entropy. So in this case, the vapor phase has the smallest slope, which has the greatest entropy.